The oil and gas industry relies on natural draft fire tubes to provide the heat for dehydrators, production units, heaters, treaters, and a wide range of other process equipment. Field tests of fire tubes yielded combustion efficiencies ranging from 18 to 50%, depending on size, operating mode, and service. Generally, an efficiency of 25 to 50% is normal for large-diameter fire tubes. Engineered Concepts' Automatic Secondary Air Control, or ASAC system, optimizes combustion efficiency to reduce emissions and fuel costs by 50% on average. Best of all, the ASAC is self-adjusting, regardless of ambient conditions, 24 hours a day. The ASAC system limits the secondary air entering the combustion chamber, resulting in a significant improvement in combustion efficiency. Field test efficiencies of the ASAC are most often reported as 75% or more. On that basis, it is not unreasonable to expect reductions in fuel consumption ranging from 30 to 75%, depending on the combustion environment. The ASAC decreases carbon dioxide and NOx emissions by 50% on average, while reducing fire outages by providing more efficient and reliable burner operations. Engineered Concepts' ASAC system is field-proven, and hundreds have been retrofitted to existing oil field production and processing equipment or incorporated into new equipment packages. Fire tube heaters typically use low-pressure partial pre-mix burners in which part of the air required for combustion, the primary air, is drawn into the burner and mixed with the fuel prior to reaching the flame at the burner tip. Secondary air drawn through the fire tube by stack draft provides the additional oxygen required for complete combustion of the fuel. The exact ratio of air, primary and secondary, required to burn a fuel is called the theoretical air. Ideal combustion at this ratio would yield an exhaust gas with no oxygen or combustibles. Any secondary air not required for combustion is excess air. Excess air decreases the efficiency and is counterproductive to the combustion and heating process. Excess air wastes money from your operations by decreasing fire tube heating efficiency in two ways. 1. The heat used to warm the excess air to exhaust temperature is lost out the stack. And 2. Excess air lowers the flame temperature. Excess air of only 16.2%, 3.4% excess oxygen, lowers the flame temperature by about 260 degrees, thus reducing the temperature difference between the flame and the process so that less heat is transferred per unit area in the fire tube. The available heat chart illustrates the effect of excess air on overall combustion efficiency. Depending upon the process loads and the diameter of the fire tubes with uncontrolled secondary air operate with stack exhaust gas temperatures ranging between 600 to 1100 degrees and with excess air of 100 to 600% or 11 to 18.2% excess oxygen. This operating envelope covers efficiencies ranging from less than 10% to 60%. Large diameter fire tubes tend to be on the low end of the efficiency range. The orange shaded area on the available heat chart illustrates the typical efficiency range for natural draft fire tubes with uncontrolled secondary air. Field performance tests have been conducted on various sizes and types of equipment to determine typical combustion efficiencies. Large diameter fire tubes generally exhibit lower efficiencies than small diameter fire tubes because a large fire tube draws more excess air due to stack draft in proportion to its cross-sectional area, a function of its diameter squared, whereas the ability to deliver energy from the fire tube to the process is in proportion to the surface area, a function of the diameter. Therefore, large fire tubes draw larger proportions of excess air and are more prone to lower heating and combustion efficiencies. Controlling excess air increases combustion efficiency. The temperature of the stack exhaust is a good indicator of the energy wasted by inefficient combustion because any heat contained in the exhaust is not used in heating the process, and cooling the exhaust is a primary goal in attaining increased efficiency. The best way to cool the stack exhaust and increase combustion efficiency is by controlling the excess air in a narrow band of about 10 to 25%, 2.1 to 4.5% excess oxygen. Reducing the excess air to this range will cool the exhaust gases and increase the overall combustion efficiency to 75 to 80% using a higher heating value basis, as illustrated by the blue region of the available heat chart. In addition to operating with uncontrolled secondary air, many fire tubes waste valuable heat operating in off-on or snap-acting modes. As shown in this graph, during the off cycle, the stack continues to draft ambient air into the fire tube, thereby cooling the combustion process. Large quantities of heat are lost from the process during the off cycle. Equipment designed with multiple fire tubes suffer this negative heat exchange effect if one or more of the fire tubes is idle. The ASAC controls the flow of ambient air into the combustion chamber while the fire tube is idle to eliminate this negative effect. This feature also reduces potential fire outages in field equipment. The automatic secondary air control system regulates the secondary air in direct proportion to the burner fuel pressure. Pressure from the burner fuel manifold operates the air control valve to regulate the amount of secondary air flowing into the combustion chamber. The air control valve is adjustable to compensate for fuel composition and altitude, ensuring the optimum proportion of secondary or excess air under all operating conditions. Once adjusted, the ASAC maintains a constant fuel-to-air ratio across the full burner firing range by moving in response to changes in the burner fuel pressure. The system is designed to maintain the excess oxygen at 2% to 5% across the entire firing range of the burner, as shown in this stack oxygen content comparison between an ASAC-equipped unit and an uncontrolled fire tube. Even when the fire tube is idle, the ASAC system regulates the airflow through the fire tube. This feature virtually eliminates the cooling effects associated with idle fire tubes and allows use of multiple staged fire tubes to accommodate the process load in the most efficient manner while still maintaining a high overall combustion efficiency. The improved efficiency gained by controlling excess oxygen and eliminating cooling effects when the fire tube is idle is illustrated in this efficiency comparison over a 20-minute time period. The ASAC system is not limited to large process heating operations. Any natural draft fire tube 12 inches in diameter and greater will realize significant fuel savings and emission reductions automatically. Engineered Concepts engineers and fabricates a wide range of revenue-generating production equipment from the wellhead to the pipeline. With emission-free dehydration and a host of various vapor recovery options, operators can now capture emissions through application of innovative ideas for the maximum environmental and economic impact. Visit www.engineeredconcepts.com for more details.